Welcome all. Myself K. Sirisha, working as Assistant Professor in Mechanical Engineering Department in MPR College of Engineering and Technology. Today, we discuss about the topic derive the expression for steady flow energy equation. So, derive the expression for steady flow energy equation. Already we solved in previous class, but I can recall again. I can recall it. So, study flow energy equation. What is steady flow energy equation? So if the fluid flows at constant rate through the system, the flow is said to be steady flow. So the properties of the fluid where it is flowing is constant is known as steady flow process. Steady flow. So for the derivation of steady flow energy equations, following assumptions are made. So we want to derive the steady flow energy equation. So we will take some assumptions for made the steady flow energy equation. So what are those assumptions? Are the fluid passing through the system is uniform in composition. So the composition is the same throughout the system. Work and heat are only interactions between system and surroundings, and the mass flow rate of the fluid through the system remains constant if entering of mass m1 is equal to out of mass m2. So both are same. So that is called the mass flow rate of the fluid through the system remains constant. And next, the state of the fluid at any point which is given by the properties of the system is independent time. That is the meaning of if time changes, the properties does not change. That meaning of that the properties of the system remains constant. Okay, next, kinetic, potential and only flow energies are considered in the analysis. Here in steady flow energy equation, kinetic, potential and only flow energies are considered in the analysis. So let us see the figure first. So in a figure represent the open system where both mass and energy transfer takes place between the system and the surroundings. This is the system, and out of the system we consider as surroundings. So let the figure represent an open system where both mass and energy transfer takes place between the system and the surroundings. The fluid the fluid enters the system through the inlet section. This is inlet section 1 1. The fluid enters here and leaves the system through the outlet section. This is the outlet section. So fluid enters and fluid out. So it has properties like P1 is nothing but pressure, A1 area, V1 velocity, and P2 A2 V2. So this is the steady flow process for open system. So this is the datum line. So where is the system above from the datum line? So here the inlet, the elevation of inlet is Z1 and outlet is Z2. Okay, so let the suffixes 1 and 2 of the following properties represent the same at inlet and outlet sections respectively. Here at inlet section we called as 1 A1 P1 V1, and outlet section we called as P2 A2 V2. Okay, let here P specific volume meter cube per kg units, and P pressure of the fluid Newton per meter square, velocity units meter per second, mu U not mu U specific internal energy of fluid joule per kg, and Z is nothing but height above the datum line. So this is Z, height above the datum line. Now let Q and W be the amount of heat supplied and work done. So the units of heat supplied and work done is same, joule per kg by the system. So both are by the system. So here Q by the system and work by the system only. Okay, sorry, let Q and W be the heat supplied. Here he is the Q supplied, Q is the heat supplied and work done by the system. That is both are positive. Both are positive. Both are positive here. So total energy at inlet section is given by the sum of internal energy, kinetic and potential energy, and heat supplied and work also. So it in inlet section. Here consider what are the points we have: pressure, area, velocity, and we have datum of height. So for how to calculate here, the different types of energies here. So at the inlet we have heat is supplied. At the inlet we have heat is supplied, and by taking with velocity, fluid is flowing. So we have kinetic energy also. With respect to distance, potential energy is mg jet. Okay, and we have pv. So pv and internal energy also, and a specific internal energy also there. So specific internal energy also, the properties of fluid. So finally at inlet section we have internal energy plus pressure into specific volume plus v1 square by 2, that is nothing but kinetic energy, plus z1 into g, that is potential energy, plus at inlet the heat is supplied. So this is the total energy at the inlet section. And next, similarly at the outlet section, total energy is given by the equation u2 plus p2v2 plus v2 square by 2 plus z2g plus w122. So w122 is the work done by the system, q122 is the work heat was supplied to the system. So this is the inlet section and outlet section of total energy of equation. According to first law of thermodynamics, what it says, total q is equal to total work done. So that is the first law of thermodynamics is. At the same time, total inlet is equal to total outlet. So here, so inlet is equal to outlet. So what is inlet? u1 plus p1 v1 plus v1 square by 2 plus z1 g plus q122, that is nothing but heat supplied, is equal to, so inlet is equal to outlet u2 plus p2 v2 plus v2 square by 2 plus z2g plus w122. What do you know? Since enthalpy is nothing but the summation of internal energy and product of pressure into velocity, pressure into velocity. Okay, so H is equal to U plus V, internal energy plus pressure into velocity. So we can write as U plus P1 V1 called as H1 plus V1 square by 2 plus Z1G plus Q122 is equal to, here also U2 plus P2 V2 we can write as H2 plus V2 square by 2 plus Z2G plus W122. The above equation represents the steady flow energy equation per unit mass. So if it is a per unit mass, we will multiply m on both sides. So finally this is our steady flow energy equation. This equation is very important regarding the steady flow energy problems. So you have to remember this steady flow energy equation. So finally this is our equation. Okay, steady flow energy equation. And also we have derived the energy balance equation of a because of in open system we have so many of examples like turbines, nozzles, diffusers, heat exchangers. Those are all the examples for open system, and this open system apply the energy balance equation for different types. So first we can derive the energy balance equation of a steam nozzle and heat exchanger. So here it is the steam nozzle. So steam nozzle is used in steam turbine power plant to convert pressure energy of steam into kinetic energy of steam. So pressure energy of steam to kinetic energy of steam. Here this is a convergent and divergent nozzle. Here it is a steaming, like it has a properties of pressure, enthalpy, specific volume, specific volume, P2, V2, H2, nothing but, sorry, this is a velocity, and this is a boundary, and this is a adiabatic wall. So if it is a adiabatic wall, there is no heat transfer takes place between the system and the surrounding. That is the meaning of Q is equal to 0. If Q is equal to 0, there is no work done on the system. There is no work done on the system, nothing but there is no work done between the system and surrounding. That is nothing but W is equal to 0, Q is equal to 0. Here there is no any datum not given in the given figure. So that is the meaning of there is no elevation. That is the meaning of potential energy also 0. So applying Bernoulli's equation applies Bernoulli's equation for 1 and 2. So for 1 and 2, okay, high pressure, high enthalpy steam passes through a resin. Here, high pressure, high enthalpy passes through a resin nozzle. This causes decrease in pressure. So when it passes, it is a convergent and it is a divergent. When it passes, a high pressure and enthalpy of steam is passes through this convergent, and after divergent, it decreases its pressure and drop the enthalpy in nozzle. This causes decrease in pressure and drop in enthalpy as the flow accelerates. So applying energy equation to the system per unit mass flow. So P is equal to 0, W is equal to 0, Q is equal to 0. Here, so look at the steady flow energy equation. So here look at the energy equation. What we know, first of all, there is no potential energy because of Z1G, Z2G 0, and next there is no heat transfer because of adiabatic. There is no work done because of there is no heat transfer takes place between the system and the surrounding, so no work done. So finally, what the equation we get, Q by M, capital Q by M is nothing but a small q. Small q is equal to capital Q into M. So we replace capital Q into M with this small q. So here, so H1 plus because of small q is 0, so H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. And finally, our velocity is at outlet is equal to root of V1 square plus 2 into H1 minus H2 meter per second, because of it is velocity. V1 is velocity of steam at inlet meter per second. V2 is velocity of steam at exit meter per second, and H1 minus H2 is the enthalpy drop. So finally, this equation you have to remember for the problems of nozzle by using steady flow energy equation. Next we look at energy analysis of heat exchanger. Here, why are using heat exchangers? A heat exchanger is a device used to transfer heat from one fluid to another fluid. Heat exchanger can be a condenser or evaporator. Here, the heat exchanger is used to transfer the heat between one fluid to another fluid. Heat exchanger may be condenser or evaporator. So condenser, it may cools, and evaporator, it may heated. So in heat exchanger we have two types, condenser or evaporator. If we consider condenser, this is the condenser. So here we're using coolant in and coolant out. So steam in and steam out. If you have the steam is very hot with high temperature, whenever the coolant is flowing through it, so this heat is taken from the steam in. Finally, the steam may condensed at the outer. So here heat is the temperature 10 degrees for example, and out of the coolant fluid is 30 degrees. Because of coolant fluid increases, steam temperature decreases. That is the reason the whenever the steam temperature decreases, it may condense. So when it is used to condense steam in steam power plant using water as a cooling medium. In power plants, condensers using water as a medium. In refrigerator, air is used as a cooling medium. And there is no change in potential energy and kinetic energy. So if there is no change in potential energy and kinetic energy, there is no work done by the system. That is the meaning of potential energy 0, work done 0, and there is a change in the energy. So totally delta E 0. So if we consider steady flow energy equation again, so there is no potential energy. So Z1G, Z2G 0. There is no potential energy, and there is no potential energy, there is no work done. And there is no energy. Finally, our equation, actually H1 plus Q we have in this equation. Actually, Q into M is nothing but small q. Actually, here we have plus Q, H1 plus Q is equal to H2 plus W. We have the equation got in our heat exchanger, but we take negatives here. Why? The negative sign with Q is taken because the heat is lost by the coolant while passing through the condenser. So that is the reason we put a negative sign with for Q. So H1 minus Q is equal to H2. Sorry. So finally, our heat transfer Q is equal to H1 minus H2 for a condenser. And if you take evaporator, here it is also a heat exchanger. Use it to absorb heat from the surroundings. The liquid refrigerant passes through evaporator coil, receives heat and leaves vapor refrigerant. Actually, this is a heating coil. This is a heating coil. Here, a liquid refrigerant is passing through the heating coil. This heat is taken from the liquid refrigerant, and finally we get the vapor refrigerant. So here heat is absorbed. Heat is absorbed from the heating coil, and liquid is converted to vapor. So what is the heat transfer? Is nothing but H1 plus Q is equal to H2. Q is equal to difference of enthalpy. For condenser, Q is equal to H1 minus H2. For evaporator, Q is equal to H2 minus H1. That is heat exchanger, and above is nozzle. In nozzle, we are derived velocity, and in heat exchanger we derived heat transfer for condenser and evaporator. And next, make an energy analysis of the steam turbine and rotary compressor. So we derived nozzle, heat exchangers, nozzle heat exchangers. Now we are going to make the energy analysis of steam turbine and rotary compressor. So steam turbine and rotary compressor. First of all, energy analysis of the steam turbine. In a steam turbine, steam is passed through the turbine, and a part of its energy is converted into work in the turbine. This output of the turbine runs a generator to produce electricity as shown in the figure below. The steam leaves the turbine at lower pressure of temperature. It is a power producing machine. It is one type of prime mover. Here it is a diagram. Here it is a diagram. Here, steam from boiler is taken into the turbine, and in turbine blades are rotated, and when blades are rotated, it rotates the shaft. When shaft is rotated, it is coupled to electric generator. In electric generator, we got the electric power. So when this turbine, so the rejected steam is going to the condenser. So energy equation in steady flow for turbine. What do we know the steady flow energy equation? M dot into H1 plus V1 square by 2 plus GZ1 plus Q dot is equal to M dot into H2 plus V2 square by 2 plus G into Z2 plus W. So this is our steady flow energy equation, and this steady flow energy equation is applying for turbine system. What we got here, there is no elevation, so that is why there is no potential energy. Z1 is equal to Z2, so delta Z is equal to 0. So finally, what the equation we have, M dot into H1 plus V1 square by 2 minus Q is equal to M2 dot H2 plus V2 square by 2 plus W. Why? Because the sign of Q is negative, because heat is rejected. The work done, or the sign of work W is positive, because work is done by the system. You can observe here one thing. Here the steam into the system, the work into the system, the shaft is rotated, and and it is coupled to shaft is coupled to the electric generator. We got the power. Here work done by the system. Our here work it is a power producing device. Okay, so it is a prime mover, so that is why our work done is positive. Here heat is rejected from the steam turbine, so that is why Q is negative. So that is the reason we make the Q is negative. So finally what is the equation we got? H1 is equal to specific enthalpy at inlet, M dot is equal to mass flow rate of steam. So why? Because we put the dot above the M, That is the meaning of kg per second. So when the time is given, we put a dot above the term. So m dot is equal to mass flow rate of steam kg per second, and v1 velocity of steam at inlet meter per second. So the units are very important when while we do the problems. So if you don't know the proper units, we do not solve the problems properly. So definitely you can learn the units of each and every term, students, and work done per second, nothing but units are joule per second. Here the joule per second we know also known as water. Joule per second is nothing but water. So first of all, and energy analysis of the rotary compressor. Here also the same thing. In electric generator, here air is compressed in the compressor. Here air is passed through the compressor. Here air is compressed. Here gas in. Here it is compressed and gas out. So P1 is the inlet pressure, P2 is the outlet pressure. A rotary compressor is a machine which compresses air and supplies the same at moderate pressure and in large quantity. It consumes rate of work, that is power consuming machine. The figure given below shows rotary compressor. So what do we know the Stanislav energy equation? We know the Stanislav energy equation. So what we know the terms of compressor. Here also potential energy is 0. So m dot h1 plus v1 square by 2. Here also we take negative because of q is taken as negative as heat is lost from the system. When it is compressed in the compressor, heat is lost from the system, and work is taken as positive, and work is here also the work is taken as positive. Work here also same. What the equation we got of turbine, it is same to the compressor also. And next now we look at some problems. In a turbo machine handling an incompressible fluid with a density of 1000 kg per meter cube, the conditions of the fluid at the rotor entry and exit are as given below. The inlet conditions are: pressure is equal to 0.05 megapascal, velocity is equal to 15.5 meter per second, height above datum is equal to 2 meter. If the volume flow rate of the fluid is 40 meter cube per second, estimate the net energy transfer from the fluid as well. So this is our data. So inlet pressure P1 is equal to 1.15 megapascal inlet pressure. So the because of turbo machine, so take the open system. So this is inlet and this is outlet. This is our datum. Entry points P1, V1, Z1, P2, V2, Z2. So with respect to datum Z1, with respect to datum Z2. Inlet pressure 1.15 megapascal. In case we replace with mega, nothing but 10 cube into 10 cube. So 10 cube as kilo. So 1150 kilopascal. Inlet velocity 30 meter per second. Inlet height above the datum. Inlet here in a turbo machine handling the incompressible fluid with the density is given. The conditions of the fluid at the rotor entry and exit are given below. The inlet pressures of here 0.05 replace 1.15. Okay, and velocity 15 point. Velocity inlet conditions of pressure, velocity, height above the datum 2 meters. If the volume flow rate of the fluid is 40 meter cube per second, estimate the net energy flow rate. So we are going to find out the net energy is nothing but W. We are going to find out. Here some values are given wrong, so take these values only. So pressure as 1.15. Okay, pressure is 1.15, velocity as 30 meter per second, and the inlet height datum. Here height above the datum is 2 meters is given. So we will take here some data is missing. So taken this data and solve the problem. So here our Z1 value is 10 meters. So at inlet, and what the terms are given, that is Z1 and P2. So this is a data already given. Some data is wrong. So take this data, do the problem. Okay. So P2 is 0.05. Sorry. So sorry. some values are changes. Inlet datum 10 meters and outlet pressure 0.05. This datum only you considered. The problem given wrong. So that by taking this data, solve the problem. And outer pressure P2 0.05 megapascal, mega into nothing but 10 cube into 10 cube. So 10 cube is kilo, so 50 into kilopascal. Outlet velocity, so this is our outlet velocity, 15.5 meter per second. And outlet height above the datum, here this is 2 meters, and this is Z is equal to 10 meters. And flow rate m dot is equal to 40 meter cube per second, so 40 into 103 kg per second. So density is equal to 1000 kg per meter cube for this system. Energy transfer from liquid as heat, Q is equal to 0. This is the energy equation. But substitute all the values here. Find out the work transfer. Here Q is taken as 0. For this system, energy transfer from liquid as heat, so there is no heat transfer. Q is equal to 0, and remaining all the values put here. We got the work transfer. Some here data is missing. By using this data, we do solve the problem. Okay, and next go to another problem, and finally substitute all the values here. We find out the value work done W, and see another problem. Same like in a steady flow apparatus, 135 kilojoule of work done by each kg of fluid. That is nothing but W given. Specific volume is specific volume, pressure and velocity, and the mu pressure V given. Inlet that is nothing but Z1, and discharge pipe is at floor level. The discharge conditions 0.62 meter cube kg, 100 kilopascal and 270 meter per. That is nothing but discharge conditions between outlet. The total heat loss between inlet and outlet, Q is given. In this flow, determine specific internal energy increases or decreases. That is nothing but delta U. We are going to find out that delta U. Specific internal energy is nothing but delta U, if it is increases or decreases. So work done by each kg of fluid, W given. Total heat loss, because of heat loss we put the sign of negative. Okay, loss is nothing but negative. Properties of fluid at inlet, specific volume mu 1, not velocity. Meter cube per kg is nothing but specific volume, 0.37 meter cube per kg. Pressure 600 kilopascal. Velocity 16 meter per second. Potential head for Z1 is equal to 32 meters. And properties of fluid at discharge, specific volume V2 mu2 is equal to 0.60 meter cube per kg. Pressure, velocity, potential head. Because of there is no value given for the discharge, so that is why Z2. So here it is a data diagram like that. Because of Z1 with respect to datum we have some value, but here there is no value, so that is why we put the value of Z2 is 0. Here it is the inlet and this is the outlet section. So applied steady flow energy equation. So H1 plus V1 square by 2 plus G into Z1 plus Q is equal to H2 plus V2 square by 2 plus G into Z2 plus W. This is the energy flow equation. So what do you know? U1 plus P1 mu1. Here mu1 is nothing but specific energy. U1 is the internal energy plus V1 square by 2 plus G into Z1 plus Q is equal to H is equal to U plus V. Okay. So here we rearrange the equation like that. U1 minus U2 is equal to P2 V2 minus P1 V1 plus V2 square minus V1 square by 2 plus G into Z2 minus Z1 plus W minus Q. Okay, here we know all the values. Here W is given, Q is given, V1 is given, V2 is given, Z2, Z1, everything, every data are given from the above problem. So put all the values here. Put all the values here. We got that U1 minus U2 is equal to 20.636. That is U2 minus U1 is equal to minus 20.636. So specific internal energy decreases by, because of change in internal energy, there is nothing but U2 minus U1. So that is why negative sign. So negative sign indicates that specific internal energy decreases by 20.636 kilojoule per kg. Okay. First of all, we have to remember what is the steady flow energy thermodynamic cycle consisting of three processes. So we have three processes. This model problem already we done, but there is a little change in this problem. A gas undergoes a thermodynamic cycle consists of three processes beginning at an initial state P1, V1 and U1 is equal to 512 kilojoule. The process are as follows. Here we have P1, V1 and internal energy for state 1. But here are some conditions are given in the problem. What are those conditions of conditions are? So process 1 to 2. So that is nothing but compression with PV is equal to constant. So PV is equal to constant is nothing but isothermal process. So we know it is a compression with isothermal process. Okay, and isothermal process P2 2 bar U2 690 kilojoule. Already for state 1 P1 V1 U1 given, for state 2 because of compression 1 to 2, so P2 U2. Process 2 to 3 W 2 to 3 is equal to 0. So whenever the work done is 0, absolutely it is a constant volume process. For a constant volume process on PV diagram, the work done is 0. So 2 to 3 process is constant volume process, and heat is heat transfer minus 152, that is nothing but heat loss takes place. And process 3 to 1 W1 to 1 is equal to 55 kilos. There is no choice because of there is no process, so there is no isothermal like that. So we have one choice is nothing but constant pressure process. So for given that initial pressure P1 1 bar, initial volume V1 is equal to 1.5 meter cube, internal energy U1 is equal to 512 kilojoule. So students observe, I want to tell you one thing, what are the data given? First of all, when you are going to solve the problem, first you start with given data. What the data given from the above problem. So if you write all the data in proper manner, you will understand each and every point from the problem. Okay, so for your given data is initial pressure, initial volume, initial internal energy given. So first of all 1 to 2 process is isothermal process, and it process is compression. When it is compression is nothing but volume decreases. When it is expansion, volume it increases. Here compression process 1 to 2, so V1 V2 V1 to V2, that is nothing but volume decreases. So this is the process 1 to 2, and next work done 0 is nothing but constant volume process 2 to 3, and next 3 to 1 takes place nothing but a constant pressure process. So now we are going to heat transfer of each process. So from above figure, so take all the diagram on PV diagram. So according to first law of thermodynamics, what do you know for a process? Actually, the first law of thermodynamics for a process is Q is equal to delta U plus W. And first law of thermodynamics for a cycle is integral, cyclic integral of Q is equal to cyclic integral of W. Okay. First law of thermodynamics for a process is nothing but Q is equal to delta U plus W. At the same way, according to first law of thermodynamics, for a cyclic process is nothing but cyclic integral of Q is equal to cyclic integral of W. Okay, for process 1 to 2, for process 1 to 2, for what do you know for a process 1 to 2? Actually, what do you know? Q is from first law of thermodynamics. Q is equal to Q1 to 2 process U2 minus U1 plus W1 to 2. All U2 minus U1 is equal to, already we know the actually for Q1 here U2 is given P1 V1 U1. Okay, for process 1 to 2, first now you are going to what is 620 here. Okay, first of all U2 minus U1 is equal to, this is U2 minus U1 is equal to 690 minus 512. So find out U2 minus U1, and next we are going to find out actually 1 to 2 process isothermal compression process. So what do you know? Isothermal PV is equal to constant, P1 V1 is equal to P2 V2, from P2 is equal to P1 V1 by P2. So we found out the value of V2. What do you know the work done for isothermal process? P1 V1. We have to remember each and every point what the process are going. Already I have told in the previous classes what is the work done for isothermal, what is the work done for constant pressure, what is the work done for constant volume. We solved some problems also. So we have to remember what are the derivations regarding the process. Okay, for isothermal process, work done is nothing but P1 V1 log of V2 by V1. So substitute this value, we found out the value of work done. The negative gives nothing but work done on the system, and Q. So substitute the W1 to 2, U2 minus U1. We got the heat transfer between 1 to 2, Q1 to 2. And next process 2 to 3 is a constant volume process. For 2 to 3, W1 to 2 to 3 is equal to 0. For a constant volume process, V2 is equal to V3. Okay, so 2 to 3 is a constant volume process, V2 is equal to V3 W. Sorry for the interruption. Okay, for 2 to 3, for 2 to 3 process, W2 to 3 is equal to 0, Q2 Q2 to 3 is equal to delta U, delta U. So first of all, because of work done is equal to 0, actually Q is equal to delta U plus W. Your work done 0, so that is why Q2 to 3 is equal to delta U. So U3 minus U2. Okay, so we know already Q2 to 3 already given, given in the above problem. What is Q2 3 minus 152 kilojoule? Okay, minus 152 kilojoule. So put minus 152 kilojoule here, minus 152, U3 minus U2 already found U2 here. Already we know the value of U2 from given problem. So put the value here, find out U3. For process 3 to 1, delta U is equal to U1 minus U3. U1, you know already U1, so put the value of U3. Next, delta U is equal to minus 26 kilojoule. And Q3 1 delta U plus W3 to 1 already given W3 to 1 from above problem. Delta U is equal to minus 26 kilojoule, and we have Q3 to 1 process. So from the above problem, he asked only heat transfer between 1 to 2 and heat transfer between 2 to 3 to 1. 3 to 1. Thank you, students.